Yes. So hi everyone. My name is Nima Pahlevan. I'm with Science System Applications, a government contractor company. I'm based at NASA Goddard Space Flight Center, Greenbelt, Maryland. It's been over 8 years that I've been working for NASA Goddard Space Flight Center here. So I'm working with a group of young, smart scientists to essentially enable aquatic remote sensing science through processing of satellite data sets. So today I'm very happy and excited to share with you some of the basics of remote sensing of water quality. And please jump in if you have any questions. But let's just go ahead and get us started, Terry. Okay, so just to give you an idea of what I'll be talking about today, I'll first start by talking about the role of remote sensing in water quality. I'll give you a brief theoretical background of remote sensing of water quality, and then I'll jump into how the water quality maps can be generated from satellite observations. That would include discussions about different satellite sensors, a key processing step referred to as atmospheric correction. Then I'll switch over to algorithms for estimating water quality parameters after atmospheric correction, and then I'll talk about validation and product availability. And then I'll finish up with a summary. Next. Okay, so this, of course, this is a PDF version. It was meant to be a transition, but I guess you get the whole picture once. So here's Lake Titicaca, August 3rd, 2014. Really, what we're tasked to do as scientists, as remote sensing scientists, is to convert a boring-looking satellite observation to the left, or image, to information, useful water quality data sets per pixel across the image. So what you can see on the right is a chlorophyll A concentration that has been produced from this Landsat observation, Landsat 8 observation from the left. And you, of course, can see the variability in chlorophyll A, which is basically the concentration of near surface concentration of chlorophyll A across the lake. So if you compare this realm of sort of a significant amount of information that is provided through satellite with field observations, you can see that it significantly facilitates the way we can observe eutrophic condition or trophic states across a large lake like Lake Titicaca. So there is, of course, you guys are quite savvy as far as field observations and field measurements go, but it's significant amount of time and money involved in collecting data to be able to capture all the dynamics that we're seeing across this lake. Next. I basically just indicated what I was going to say here, but overall, satellite covers a large area. It gives you a quick exposure, a synoptic view of concentration of chlorophyll A in this instance. However, in general, they're considered complementary to field sampling. The satellite observations are not there to replace field sampling. Rather, they're there to augment and complement what's happening within the field data collection, and essentially to help ultimately to improve decision making. The one caveat here is that while satellite data sets and products are extremely helpful with that decision making, they lack the rigor and accuracy that you can obtain from field observations, obviously. So again, I would like to emphasize this. The goal here is to complement what's being observed in the field with all your field techniques that you are familiar with. Next. Can you click? I don't think this is an animation. It's supposed to work, but it's a PDF, but it's okay. Essentially, my intention here was to show that how a satellite essentially captures dynamics of water quality across the globe over open ocean, coastal, and inland waters. So generally, we tend to use satellites that are placed in low Earth orbits. So these are near circular orbits or polar orbits. Each orbit takes about 90 minutes to essentially cover a wide swath of observations under satellite uh, uh, track. And then on board these satellites, there's basically cameras, sophisticated, well-calibrated satellite cameras that would enable data collection across the globe and as the Earth rotates from west to east. Next. So what's the main quantity of interest in remote sensing of water quality? So what we basically measure from satellite is nothing but water color, which is the division of water leaving radiance, or amount of photons that leave body of water to the downwelling solar irradiance, or to total solar light, or light available just above the water. So it's the division of these two parameters, meaning water leaving radiance and downwelling irradiance, downwelling solar irradiance, is referred to as RRS, or remote sensing reflectance. It's basically contains information about near surface concentration of constituents like chlorophyll A, like total suspended solids, etc., etc. So as this is Lake Erie, captured by Aquamodis, one of NASA's satellites. And here's my attempt to show you the correspondence of different water colors with their associated remote sensing reflectance, or RRS. As you can see, these RRS spectra, just so you know, that they're shown from within the visible band spectrum, from 400 to about 700, 800 nanometers, so just a little into the near infrared region. And the different water colors are sort of reflected in different RRS spectrum shapes and magnitudes. So, for instance, if you look to the all the way to the right, you see a blue water on the east portion of the Lake Erie, and the water happens to be peaking. The spectrum appears to peak around the blue part of the spectrum. So it's simply indicating that you're looking at a blue water. So further down, we're looking at towards like a southwestern portion of the lake. We're looking at surface scums, which are similar to vegetation. And as you can see, we also see a significant peak that plateaus in the near infrared, meaning that you're basically looking at vegetation over water, and that's basically a surface scum. You move further to the west, where there's a sediment concentration, high concentration of sediment in the water due to resuspension events and wind events, and you see the corresponding spectrum showing a higher amount of reflectance, or photons coming out of water in the red and green portion of the spectrum, indicating that there is potentially a significant amount of particles in the body of water. Let's see. To the mic. Okay, sure. So hopefully you got the idea. What satellite measures is basically a color of water that it's being used to retrieve various parameters of interest, which I'll speak about in the next few slides. Next. Okay, so here is how things work. Happy photons from sun penetrating the water column. The penetration depth varies across the board, from ultraviolet portion of the spectrum, from the purple a row there, all the way to the red and the infrared portion of the spectrum. The maximum penetration depth is known to be around the blue band for about 490 nanometer region. After this penetration happens, penetration of light in the water, then what happens is a scattering and absorption of this amount of light by various constituents, including algal particles, non-algal particles, organic matter, etc. You name it. Various, constituents essentially can absorb and or scatter light differently. The cumulative effect of this absorption and backscattering is going to essentially be measured by the satellite, depending on where the satellite is. So again, the key takeaway here is that what's being observed from satellite is a quantity referred to as water leaving radiance, or if you divide that by downward leaking radiance, it will be RRS. And that RRS is really what's being used and what's being essentially retrieved from original satellite observations to get to, say, concentration of algal particles or non-algal particles or organic matter. Can we go next? Yeah. So here are some set of parameters that can be retrieved from satellite observations. Those include pigments, including chlorophyll A or CHLA or phycocyanin like PC, or many other pigments. Essentially, from satellite directly, you can measure material or constituents that impact the color of water. And chlorophyll A and phycocyanin and other pigments are amongst those that impact color of water. Chlorophyll A, of course, has been the most important parameter. It's the primary pigment in a wide range of phytoplanktons. There is also total suspended solids, or the potentially mostly impacted, mostly formed of inorganic particles. That also can, the concentration of it and their absorption and scattering properties could be retrieved from satellites. There's also color dissolved organic matter, or CDOM, and its particularly absorption that can be retrieved from satellite. This is essentially, this parameter CDOM is directly related to carbon, amount of carbon in the water column. There's also turbidity that can easily be measured, fairly easily, it can be measured from satellite. And there's also water transparency, which can be estimated from Secchi disk depth, that can be also retrieved from satellite observation. These are just a small, it's just a very short list of different parameters that can be retrieved from satellite observations or satellite-derived RRS. So the list can go way beyond this, but these are just a few examples. Just wanted to emphasize that when we talk about all these pigments, total suspended solids and color dissolved organic matter, etc., these all correspond to near surface waters. If you ask about 10 meter or 20 meter deep, depending on the transparency of water, satellite may not be able to capture that contribution to the signal, because what satellite observes is near surface conditions, whether it's chlorophyll A, whether it's a mix of chlorophyll A and TSS, et cetera, et cetera. So the inverse modeling, can you go back? Yeah. So the inverse modeling here is, so what you see under that block of orange rectangular, back please, yes. It's RRS that you can't see, but really the gist of this lower portion of the slide is basically the goal is to estimate particulate backscattering and absorption from RRS, and this RRS really is a function of backscattering and absorption, and from this backscattering and absorption that basically satellite observes, the constituents and their concentrations can be retrieved, like pigments, like chlorophyll A, TSS, et cetera, et cetera. So, and of course, Danielle is going to be talking more about that in terms of algorithms, but really the the broad understanding of retrieving these parameters is essentially coming from the fact that RRS is a function of absorption and backscattering within water column. Next. Yeah. So you may be more familiar with other water quality indicators like dissolved oxygen, electrical conductivity, pH, nitrate, phosphorus. So these parameters shown in the red, in the green box here, these are considered non-optical proxies. They do not directly impact color of water. As a result, they can be measured directly from satellite. However, if these are correlated with chlorophyll A, turbidity, or TSS, why not? But in general, at this point, from the remote sensing science perspective, we tend to first retrieve turbidity and chlorophyll A and TSS and such, and from which potentially other non-optical proxies can be retrieved. What the maps shown on the right correspond to Laguna dos Saos in Uruguay. It's a region that we have worked with some of our Uruguayan colleagues in Ministry of the Environment. So these are a set of maps that we produced for them as part of some of our collaboration work with the Ministry of the Environment Uruguay. Next. So the end goal is to be able to produce maps from these satellite observations. I've already shown a couple to you, but to the right, you're seeing San Francisco Bay observed from Landsat 8, Sentinel-2, and Sentinel-3. And I'll talk about these different missions in a second. But really, the goal is to be able to obtain consistent maps, consistent water quality parameters from these different missions. So these observations from Landsat, Sentinel-2, and Sentinel-3 were collected nearly at the same time over San Francisco Bay to the right and Chesapeake to the left across US. Essentially, the goal is to be able to make sure that we obtain seamless products, including chlorophyll A and top row, TSS, second row, and then CDOM absorption at 404 nanometer from the different flavors of satellite missions. Next. So with this background information now, I would like to switch over to the discussion on how these satellite images can be produced and be used in your decision-making activities. Next. Yeah, so the first, essentially, we're going to be going through a list of A, B, C, D, E. And the first item here is satellite sensor. The first thing we need to understand is what kind of satellite assets are available out there. Starting, I'm showing this time scale is from 2010 and going forward towards 2025 and 2030 timeframe. But right now, what you can see is we have different flavors of satellite observations that collect data at different spatial resolutions, as well as spectral resolutions, as well as temporal resolutions. So these are coming with many different characteristics. The specific satellite systems highlighted with red come with a 10 to 30 meter resolution. That includes Landsat 5, currently Landsat 8 and 9, Sentinel-2 A, B, and C. And the ones are shown in highlighted in green are collecting data at about 300 nanometer, not nominally. That includes Sentinel-3A, B, and C, and D in the future. And then we have also a couple of missions here shown as J1 virs and J2 virs they collect data from that on a daily basis, but they're at coarser resolution from 750 meter to a kilometer. So what I'm trying to get at is that we have different flavors of satellite missions that are capable of measuring water quality. The tricky part is really how to combine different observations that provide that come with different capabilities, especially temporally, radiometrically, and spectrally. So it again depends on depending on the scale of your studies, your ecosystem of interest. You may pick and choose one or two satellite missions, but if you're looking at coastal waters, potentially all of these observations would be of use. Next. So this is my attempt to highlight the impact of a spatial resolution. Here is Great Lakes, North American Great Lakes, April 2018. The top one is generally this is a chlorophyll A map. The broader scale map is the chlorophyll A map, and the zoomed version is sort of over western part of Lake Erie from Sentinel-3, which is 300-meter resolution. The one below is from Sentinel-2, which has a 20-meter resolution. So really the value of some of these higher resolution satellite observations like Landsat and Sentinel-2 is that you will be able to obtain information from nearshore waters or smaller bodies of water. And you can see that while the two sets of maps from two different missions are quite consistent in terms of chlorophyll A values, there is more information can be revealed from Sentinel-2, especially around nearshore waters, which are quite masked and flagged by Sentinel-3. So it's just something to keep in mind, that you have to pick and choose the right satellite system and observations or products for your application. Next. So the second very important aspect of data processing, atmospheric correction. It's an extremely difficult part of the processing chain, because most of the signal that satellite measures comes from the atmospheric scattering and absorption. So in this cartoon here, my attempt here is to show that over close to 90% of the signal that satellite measures over bodies of water come from that atmospheric scattering and absorption, and you're basically left with a small fraction of satellite observation to retrieve water quality parameters. Hence, there are potentially significant uncertainties in satellite derived products. So something to keep in mind, that the largest uncertainties in current satellite products come from this process, this atmospheric correction procedure. Next. Here is just a reminder about RRS and how it's defined. But really, what satellite measures can be also measured in the field. So if you have spectrometers, you would be able to measure RRS and use that to validate the quality of satellite-derived RRS. That's what we refer to as validation, but validation of RRS, or the reflectance products, that is derived from satellite. And it's central to understanding the uncertainties in the satellite water quality products from satellites. Next. What we have here is algorithms. Essentially, I kind of touched upon it. I'll try to be quick here, but really the goal is to obtain pigments like chlorophyll A, parameters like total suspended solids, or TSS, or inherent optical properties like absorption and scattering parameters from RRS. This is a one-to many mapping. You need to come up with an inverse function to be able to retrieve these parameters. There are many, there are various flavors of algorithms to enable this sort of translation and conversion. And again, Daniel will be speaking about one specific way of retrieving turbidity or TSS from RRS spectra. So I won't spoil the whole discussion there, but overall, basically the idea is to be able to retrieve different water quality indicators, the ones that impact color of water, from RRS observations or derivatives of satellite measurements. Next. So here is just different versions of how you can make radiometric observations. It is like from, there are manuscripts that would detail all these different ways of measuring RRS or reflectance. And we can talk about it offline, but 10 different methods have been shown here, from which with which you can basically retrieve or measure RRS in the field and use that to validate how good satellite-derived RRS spectra are. Next. So as I mentioned, validation is required because of various sources of uncertainties, mainly from atmospheric correction and some from retrieval algorithms. But really the goal is to determine the quality of satellite-derived products. This can be done quantitative, and it's preferred. Essentially, you go out and take water quality measurements. Either you measure RRS if you have the radiometer and instrumentation, and if you don't have that, you essentially take water samples and take it to the lab and measure and quantify chlorophyll A or TSS or other parameters. But that has to be, water sampling has to be coordinated with satellite overpass. So we have to make sure that your data collection and your measurements are representative of what satellite measures. In most cases, we recommend plus minus 1 hour before or after satellite overpass. But in some scenarios where when ecosystems or aquatic ecosystems are quite stable, a day before and after could also work. Also, this validation can be done qualitatively by looking at time series products and essentially harnessing experts' knowledge in terms of how things vary over an aquatic system, known aquatic systems, and that could help with the validation of satellite products, if they're bogus, if they're useful, etc. Next. So we have been working on a system called Satellite-Based Analysis Tool for Rapid Evaluation of Aquatic Environments. This facilitates use of satellite-derived products. This is still in the work. This is, as I mentioned, we've been working with our partners in Uruguay and Peru to essentially have this system tested over a couple of locations across Uruguay. There are more than just this stream system that we're developing. There, I would probably say 5 to 10 different web platforms where you can obtain satellite-derived water quality products. And Danielle has a PowerPoint slide sort of showing all the resources that you can go to and get satellite-derived products. But this is something that we've been working on over the past 4 or 5 years, and we're looking into expanding this and have more countries test it out and provide feedback to us. And then hopefully at some point, someday, it will be available for the entire South America. Next. Yeah, so we do all the processing. We try to get the products, but the products eventually should provide information and should ultimately enable decision making. And this requires that us or other data providers be able to mass produce Earth observations or EO products. You need to have adequate storage to retain all the process data. You have to have the ability to process archive satellite data to create time series going back into the 80s and 90s. And the question is really how we can translate these products into actionable knowledge, and what are the ways to improve these products overall. The decision making is really on your side. End of the day, it could be just shutting off drinking waters because of significant harmful algal bloom contamination, or swim or not swim, or no animal close to the water. So this decision making could vary from for different applications, if you will. Next. Okay, so just briefly, I just want to highlight the benefits and challenges of remote sensing of water quality. It could save you money. It could allow you to do guided sampling, where and when to sample water. You can monitor hard to access water bodies. Those things are obvious. You can use satellite-derived products to report on Sustainable Development Goal 6, in particular indicators 632 and 661. The observations are quite frequent with respect compared to the field observations. The large area monitoring is enabled through satellite data, and you can identify hotspots from satellite images and try to focus your field measurements and sampling in those particular areas. Next. So the limitations include it requires a field validation. We still need to understand the uncertainties. We have some understanding of the overall uncertainties of satellite-derived products, but this has to be quantified in the field for each region, for each aquatic ecosystem. Satellite estimates may not be as accurate as field measurements. I kind of tried to highlight that earlier. There's cloud cover, cloud shadows, and haze that could also impact and limit the utility of satellite-derived products. Estimated variables correspond to near surface water column, so you should keep that in mind that we can't see the bottom. If you can see the bottom in the field, there's no way satellite can see it. So that's something to keep in mind. Product uncertainties in clear waters where bottom can be seen increase. So if you're trying to quantify chlorophyll A, TSS, or other parameters or turbidity, and if you have like signatures from the bottom, if you have bottom reflection, the retrievals of chlorophyll A and TSS could be even of higher uncertainties. Water quality variables generally encompass optically relevant parameters only. So if you desire to measure or infer oxygen, dissolved oxygen, or conductivity, or measure nutrients, you have to sort of relate those to satellite-derived pigment concentrations, or TSS, or etc. Next. So here's my last slide. It's sort of questions for you guys, ladies and gentlemen. This could trigger some of discussions within the room there, and I'll be happy to answer any questions. But overall, I think satellite-derived satellite observations have a significant value for water quality monitoring. It's being practiced across U.S. Mostly for guided sampling at this point, but overall, we wish for these observations to be used widely for various water quality monitoring and decision activities. With that, I'll